Hello students, welcome back. We're going to continue today with proteins part 3. Just a little review of what we did last time. When we stopped last, we talked about, the different levels of protein structure. We talked about quaternary structure. Don't let quaternary structure confuse you. If a protein has similar subunits, they're both called alpha subunits. If they have different subunits, they're called alpha and beta. Usually the larger one is called the alpha subunit and the smaller one is the beta. If it has two subunits and they're the same, we call that a homodimer. If it has two subunits and it's different, like alpha beta, we say it's a heterodimer. And so that's quaternary structure. Let us continue today talking about proteins. Let's figure out, well, how do you isolate a particular protein from a tissue? And so let's do that. Let's talk about that today. And so we're going to start with a tissue, any tissue here. So I'm going to zoom in here and I'm going to draw ourselves we're going to start out with a tissue. Any tissue of the body. Any body tissue here. Okay, I'm going to draw. This does not look like a typical body tissue, but doesn't matter. Okay, any body tissue we're going to start out with. So we're going to start with the tissue of the body. And the first thing we have to do to get that protein out of that tissue, we have to do something to that tissue. Let's say it's a muscle. Doesn't matter. It could be a muscle or an organ. We're going to take it has to be some sort of device we have to use. We have to take that device. Okay. Okay, we're going to take that protein and we're going to put it in this little device here. Anybody have any idea what this is? Exactly. And we need to grind that protein up. And so we got to grind up that tissue. And when we grind that tissue up, then we'll filter it and we'll just be left with our fluid. Okay. We'll filter that and then we'll end up with just our fluid here. And this will be our tissue fluid. So we're trying to our tissue fluid. Everyone with me so far? Makes sense so far? We take a tissue. It could be a muscle, it could be an organ, it could be any type of tissue. We'll grind that tissue up. What we're trying to do is get a particular protein. Let's say we want to get one particular protein. And so we grind that tissue. Let's say we want to get the protein dopamine beta hydroxylase. We're familiar with that protein. It's the one that adds the OH onto dopa. Well, no, it adds the OH onto dopamine to make norepinephrine. Okay, and so that's the protein we want to get. So we get to our tissue fluid. Now we can do several things to try to get this protein. To get the proteins out of this fluid. Because in this tissue fluid, you're going to have proteins, you're going to have nucleic acids, you're going to have carbohydrates, you're going to have lipids. You're going to have all of that stuff here. But we only want the proteins. And so usually, if you're in a biochemical lab, usually the first thing you want to do here, or one of the first things you want to do, is try to change the pH to get this protein to not be so dissolvable. Okay. Now, I'm going to draw a protein here. And this is what proteins look like. And so I'm going to put a P, and this is going to be our protein. And on the outside of this protein, if we have a very, let's say we're going to have plus charges on this protein. Let's just say there's no pH. Plus charges and minus charges. Because what type of amino acids are going to be on the outside of this protein? The polar amino acids. Make sense to everyone? Bless you. Now, what would happen to this? What would the charge of this protein be? I need you to think about it for about 3 seconds before you answer it. We're going to take this protein and put it in a very low pH solution. We're going to make a very low pH solution. A solution of very low pH. What would be the charge on this protein? Okay, I want you to think about it. I'm going to repeat the question. If you put this protein here in a very low pH, what would be the charge on the outside of that protein? Think about it for 3 seconds. 1, 2, 3. Anyone think they have the answer? It's going to be positive. Does anybody agree with that? Anybody disagree? She disagrees. One disagree. So we have two disagree. Okay. We have 2 disagree and 1 positive. The rest of you don't want to vote. In actuality, it is going to be positive. Because what's going to happen, if it's a very low pH, the protons, all those protons are going to attach here to neutralize those negative charges. And so now the protein is just going to have positive charges on the outside. Does that make sense? Remember, at low pH, protons stay on amino acids at low pH. Make sense? Now, the next question is, so this is going to be at very low pH. Very low pH. What if we take this same protein, let's put the protein over here, and it has plus charges, and it has negative charges. And now, we make the pH very high. We make the pH very high, or make the pH very basic. What's going to be the charge on this protein? It's going to be negative. It's going to be negative. And the reason is because if these are protons, when you lose these protons here, if you lose these protons, let's say they're carboxylic acids or aspartic acid, when you lose those protons, then the protein is going to be left with a negative charge. And so this is going to be a very high pH. Okay? And so we say here, and so a lot of times scientists will say this protein, this is a basic protein. And if they say a protein is basic, they're just another way of saying this protein is very negatively charged. And so this is going to be a very, or if they say a protein is acidic, it means it has a lot of positive charges on it. Kind of makes sense? Okay, now, if a protein has a lot of positive charges, okay, which one is going to dissolve more easily? A protein with a lot of positive charges or a protein with a lot of negative charges? Think about it. I'm going to ask the question again. Which protein is going to dissolve more easily? A protein with a lot of positive charges or a protein with a lot of negative charges? Okay. Think about it for 3 seconds. 1, 2, 3. Can anyone reason that out? Which one's going to dissolve more easily? Anyone? Positive. We got 1 positive. 2 negatives. 3 negatives. No one else wants to make a vote? The answer is they're going to both dissolve pretty much the same. Because if you have a negative charge, if a protein has a negative charge, the partially positive hydrogens will solvate that or hydrate that. If it has a positive charge, the partial negative oxygen on water is going to hydrate that. Now, if we don't want a protein, if we want a protein to precipitate, to come out of solution, what do we want the charges to be then? We want it to be neutral. Exactly. And that's why you go to the pH where there are no charges on the protein. And so if we have a protein here, and then the pH at which there are no charges here, or when it has an overall neutral charge, that pH is called the isoelectric point. Isoelectric point. So the isoelectric point of a protein is the pH at which that protein has a net charge of 0. And so if it doesn't have a charge, it's not going to be able to dissolve in water that well. And so what that protein, those proteins will start to do, they'll start to clump together and they'll precipitate out of solution. It has charges in different places, but the overall charge is 0 of that protein. Its net charge is 0. It's like the Zwitter ion. It's like the Zwitter ion of a protein. You know, a Zwitter ion of an amino acid has one positive charge, one negative charge, but overall it's neutral. The Zwitter ion of a protein, which doesn't exist, there is no Zwitter ion of the protein. But if you understand the concept of a Zwitter ion, that's what it is for a protein. It may have 10 positive charges and 10 negative charges, but the overall charge is 0, and so it's going to be easier to precipitate that out of solution. It's going to come out of solution very easily. Does that make sense? That's the first thing you need to understand. You want to get the isoelectric point. Now, for some proteins, however, even when you get to the isoelectric point, it still doesn't come out of solution very easily. You need to do one more thing. One more thing. And that's what I'm going to explain to you next. But does isoelectric point make sense? Shelby? Make sense? Excellent. Okay. Let us continue. Let us go to the next slide. Now, let me see. I have to always think about how I'm going to explain things to you all. Let's say we have this is our tissue fluid, and now we have it at the isoelectric point. We have it at the right isoelectric point here. And so these are our proteins here, and they're at the isoelectric point of the protein, so there are no charges, but it still won't fall out of solution. Still won't fall out of solution. Now, what happens with proteins? We can actually, if you increase, let's say we have ionic strength here. We have ionic strength. And let's say here our ion is something like guanidinium hydrochloride. Guanidinium HCl. That's what they usually use in proteins. And so what will happen here, if you increase the ionic strength or add more salts to this protein, let me ask you all. If you have a protein in a solution and you add salt to that solution, or a little salt to that solution, is that going to make that solution more polar? Well, forget about the protein. If you add salt to water, and let's say you have you have a beaker, one with just water and one with salt in it. Which one of those beakers is going to be more polar? The one with just the water, or one with the salt and the water? The salt and water, because you have all of those ions in there. Does that part make sense? Now, if you have a protein, let's say you just have a protein, and you add salt to that solution of protein, is the protein going to be more dissolvable in the salt or less dissolvable when you add salt? Which one is it going to be? Okay. Less solvable. Okay. Anybody disagree? Okay, let's say here, you have a solution here, and let's say it has 10 millimolar salt in it. And then you have another solution that has no salt, 0 millimolar salt. Okay? First question, which one is going to be more polar, the 10 millimolar or the 0 millimolar? 10 millimolar is going to be more polar. Which one will the protein dissolve in more easily? The 10 millimolar or the 0? No. Well, let's say we haven't done any isoelectric point. Just a protein. Let's say we just have a protein. Which one is it going to dissolve in more easily? The 10 millimolar or the 0 millimolar? It's going to dissolve in the 10 millimolar one more easily because it's more polar. It's more polar. And that's going to be true of all proteins. And I'm going to show you what's going to happen. And so what's going to happen here, as you add more ionic strength, this protein is going to become more and more solvable. More and more dissolvable. More and more. Now if what we want to do here, we want the protein to precipitate. We want it to not dissolve. So taking this approach, is this helping us at all? That's not really helping us, because the protein has become more dissolvable. We want it to become less dissolvable so it can precipitate away from everything else, the DNA, the carbohydrates, and the lipids. Does the rationale make sense before I give you the punchline? Make sense? Now, what's going to happen with this protein? I'm going to explain it later. It's going to keep on becoming more and more dissolvable, but at some point, it's going to stop dissolving, and the proteins are just going to fall out of the solution at a very high pH, at a very high ionic strength. And usually, that ionic strength is about 4 molar, very high ionic strength, 4 molar guanidinium HCl. So when you get to 4 molar guanidinium HCl, then the proteins are going to fall out of solution. And then you'll have your proteins, all of your proteins, separated from everything else that was in that solution. Okay? And so that's how we get the proteins away from all of the other tissue fluids. Does that make sense before I explain the why of why it came out of the solution? Does that make sense? Everybody okay with that? Kennedy? Excellent. Now, let's explain why. Why do the proteins eventually come out of the solution? Okay. And this is the reason why. I don't know how sure they are about this, but this is the prevailing theory right now. When you put a protein here, here's our protein. It has positive charges, positive and negatives. In that solution, you're going to have, oh, that's not good. If I draw this Mickey Mouse, you all know what that is, don't you? Very good, very good. So Mickey Mouse is water for us. And so we're going to have our Mickey Mouse here. We're going to have a Mickey Mouse here. A Mickey Mouse here. And a Mickey Mouse here. And so what's going to happen, the partial negative on water is going to solvate the positive charges on the proteins, and the hydrogens on the water, which is the partial positive, is going to solvate the negative charges on the protein. Okay. Does that make sense to everyone? Now, what scientists believe happens when you have a very, very high concentration of salt. Let's say you have here guanidinium HCl. Let's just make the salt. How should I make the salt? I'll just put here for the salt. I'll just put here C for the cation. What charge does the cation have? Positive. And A for the anion, which has a negative charge. And so if you have a large amount of salt, they believe what's going to happen. I know, I need to represent that some kind of way. I'm going to do it this way. Instead of drawing a lot of A's and C's, I'm going to draw one big C, which represents a lot of cations. Is that okay with everyone? And one big A, which represents a lot of anions. And so when you put a lot of anions and cations, or a lot of salt in that solution, what's going to happen? All of your water now, all of the water molecules are going to be busy. This is the concept. All of your water molecules now are going to be busy trying to solvate all of that salt. They're going to be busy trying to dissolve all of this salt here. And there's going to be no water left to dissolve the proteins. There's going to be no partial positives and partial negatives in the water to try to dissolve the protein. Now the protein is going to be left to itself. Now what the proteins are going to do now the proteins, they're going to start sticking to one another. And then they're going to fall. They're going to start making big clumps. They're going to fall out of the solution, making a precipitate. Does that make sense? Does that make sense? Excellent. And that's how you purify your protein or separate your protein from your other small compounds and your other macromolecules. Does the rationale make sense? Churro? Right, exactly. The solution has so much salt in it, it uses up all of the water trying to dissolve it. Now there's no water left to actually dissolve the protein. And so the protein is left to itself. It just sticks to the other proteins and they fall out of solution. That's the prevailing theory as to.
All the salt dissolves.
Yes, it's.
There won't be any salt left in the water, but it'll be the protein.
Exactly. All of the salt is dissolved. It's not a saturated solution. It's 4 molar. I mean, it's actually, you actually dissolve all of the salt. But because the salt takes priority, it gets to the water first. Now the proteins can't get there, and so it falls out of solution. And plus the proteins are bigger, and so it's going to be easier for them to make clumps. Make sense? Taylor? Chapman? Excellent. Makes sense, Thornton? Very good, very good. Okay, that's a very important principle there. What should I do here? Sometimes this data can be represented in a lot of different ways. And I want to show you such a chart because I want you to know what it means when you see it. Okay. And so what happens, let's say you have a protein and the protein is in a 20 millimolar solution. And so here we're going to have pH down here. And we'll put the isoelectric point is going to be here. And then this is solubility here. And we'll let this color here, we'll let red be. The protein is in a 20 millimolar solution. So if you're in a 20 millimolar solution, what's going to happen? The protein is going to be, you'll be able to dissolve the protein. The protein is going to be very dissolvable. But then as you get close to the isoelectric point, then it becomes less soluble. But then as you go beyond the isoelectric point, then it's not soluble anymore. And so that's a 20 millimolar solution. Very low, very low. And then if you have a higher, if you go to 10 millimolar, then, now if you put the protein in a 10 millimolar solution, and so what's going to happen? It's going to be dissolvable. But then, as it gets closer to the isoelectric point, it's going to be less dissolvable. And then as it leaves the isoelectric point, you're going to have more charges, and it's going to be soluble again. And this is out of 10 millimolar solution. So again, at 10 millimolar, it's not, because it's not as ionic, it's not as polar, it's not going to be as dissolvable. And then if you go to 1 millimolar, it's going to be more or less dissolvable. Less. But then it gets to a point, though. This is 1 millimolar. It gets to a point, though, and so as you can see what happens as you increase the ionic strength. This protein becomes more and more soluble in the water. Make sense? because we're increasing the ionic strength. So you go from 1 millimolar to 10 millimolar to 20 millimolar. You get more and more dissolvable. Now, but let's say we had a 10 millimolar solution. I'm going to put this in a whole different, make this in purple here. 10 millimolar. Will 10 millimolar be up here or down here? I'm sorry, 10 molar. Let's say you have a 10 molar salt solution. That's 1,000 times more than this. So is it going to be up here? Is it going to be up here where A is or down here where B is? See if you understand. So you all miss the whole concept if you say A. Because remember, if we go back a slide, remember, this I want to make sure. Once you get to a very high concentration, like once you get to 4 molar and beyond, then the salt is going to take up all the water and it's not going to dissolve at all. And so what's going to happen here, if you have 10 molar, then it's really nothing is going to dissolve. Because the water is being used up by the salt. So the protein does not dissolve. That's a lot to take in, isn't it? That's a lot to take in. This gets a lot of people. This concept, that's why I'm presenting it this way. I needed to see if you understood it. It varies with the protein, but for most proteins, once you start getting to 4 molar guanidinium chloride, they're going to fall out of solution. And so whenever you get 4 molar or beyond, anything higher than 4 molar, that protein is not going to dissolve because it's going to take up all of the waters. That's the point I really need you to get. That's the single most important point of this lecture. And you have to get that in your head. Question, read. Exactly. Exactly. All of the once you get to a certain ionic strength, like 4 molar and beyond, the salt takes the priority. Dissolving the salt takes the priority. Now there's no water. There are no hydrogen bonds left to hydrate, to make water shell, to make hydration shells around the protein. So the proteins start clumping together and they fall out of the solution. I really need you to understand that's the concept of the day. If you understand that, you didn't have to come to this lecture, but you have to get that concept. That's the main thing for today. Okay. Let's go back. Now what's going to happen? Here, this graph shows ionic strength. Okay. As you increase the ionic strength, or as you add more and more salt, you have a protein, you add more and more salt, the protein is going to dissolve more and more. You're going to dissolve the protein more and more. But eventually, you're going to get to a point where there's so much salt there that all the hydrogen bonds on the water are going to be used to dissolve the salt. Because the salt is going to take priority. There are going to be no hydrogen bonds on the water now left to try to dissolve, to make hydration shells around the protein. So the protein is going to be left to its own devices. And so the proteins start sticking to one another. They start, like the positive charge on this protein is going to stick to the negative charge on this protein. And they're going to start making big clumps. And then the proteins are going to precipitate out of the solution. And that's how you separate the proteins from everything else. Because the water gives priority to the salt rather than to the proteins. Does that kind of make more sense? Okay. This graph is one way to explain this. Now what I did on the next slide, it's the same information, just explained another way. So I'm showing you here, at low salt concentrations, the water, what's going to happen, the water is going to make a hydration shell around the protein, and it's going to dissolve the protein. However, if you add too much salt, and here we have the cation with its positive charge, anion with its negative charge. If you add too much salt, what's going to happen now, the salt is going to take priority. All of the hydrogen bonding on the water now is going to go to dissolve the salt, the cation and the anion. Now the protein won't have anything. There will be no hydrogen bonding to try to make hydration shells around the protein. The proteins will be left to their own devices. They're going to stick together, make clumps, and fall out of the solution. This slide is the same information, just explained in another way. Everybody okay with that? Excellent. Now, we're going to go to another slide. It's the same information, and it's just said another way. Here, let's look at let's make this one green. Okay. Yes, here we have green here. So now we have protein here in a 1 millimolar solution. And so what happens in that 1 millimolar solution, you're going to increase the pH, increase it, and as it gets closer and closer to the isoelectric point, then what happens? The protein, it becomes less dissolvable the closer it gets to the isoelectric point because there are fewer charges. If you increase the ionic strength to 10 millimolar, then you're going to be able to dissolve more protein. But again, as you get closer to the isoelectric point, the dissolvability is going to become less and less. So as you go from 1 millimolar protein to 10 millimolar protein, you can dissolve more protein. Make sense? If you go from 10 millimolar protein to 20 millimolar protein, you'll be able to dissolve even more. But again, as you get closer to the isoelectric point, you're going to have less solvation. But once you go beyond it, you're going to be able to dissolve more. But the whole point is, as you increase the ionic strength, you'll be able to dissolve more and more protein. However, you're going to eventually, if you get the pH really high, and that's what I'm showing here. Let's do this one in, let's do purple here. Make this one really big. Okay. Here, this is going to be 10 molar. Once you get to 10 molar salt, the protein never dissolves. It never dissolves around the isoelectric point or away from the isoelectric point. It never dissolves. And that's because at this very high concentration, all of the hydrogen bonding on the water is being used up by the salt. And there is no hydrogen bonding to make hydration shells around the protein. And so the protein does not dissolve in the solution. And this is the same information, just presented in a different way. It's the same information. As you increase the ionic strength, you increase the dissolvability of the protein. But you eventually get to a point where the protein doesn't dissolve because all of the hydrogen bonding has been used up by the cation and the anion. Does that make sense? Well, it just depends. As you go away from the isoelectric point, then it's going to become more dissolvable. Oh, the question was, does the protein become more dissolvable at a high pH or a low pH? It's neither high nor low. It's just away from the isoelectric point, it's going to be more dissolvable because you're going to have more charges. But when you get to the isoelectric point, you have fewer charges. The protein is neutral there, so it's going to be less dissolvable there. And so if you want to precipitate a protein from solution, you need to do two things. You need to find out the isoelectric point and put your buffer at that isoelectric point, and then you need to add some 10 millimolar or 6 millimolar guanidinium hydrochloride to precipitate it out of solution. And that's how you separate a protein from everything else that's in a tissue fluid solution. Does that make sense? Gonzalez, you seem perplexed? Everyone okay with that? Okay, let's see. Put your notes away. Let's see what kind of questions I can ask you today. I'm going to have to ask you something today because last time, I don't even know. Did anyone see the last video? This didn't work last time. I don't know why. Okay. Let's see here. Let's say we have a protein. We have a protein. That protein has an alpha subunit and 2 beta subunits. What type of protein is that? Okay, I heard heterodimer, I heard a heteroquat, and a tertiary. A protein has an alpha subunit and 2 beta subunits. What type of protein is that? A heterotrimer. A heterotrimer. Very good. Very good. At which, under what conditions are proteins more dissolvable? At a very low pH or a very high pH? Okay. A low pH or high pH? That one first. High, low, high. Right. It doesn't matter. It doesn't matter what the pH is, because if you have a very low pH, there are going to be a lot of positive charges. You have a very high pH, there are going to be a lot of negative charges. And they're both going to dissolve in water. It doesn't matter. Under what conditions or at what pH are proteins most dissolvable? I'll ask that. At what pH are proteins most dissolvable? Most dissolvable. At what pH are proteins most dissolvable? Okay, you say it's whichever one is closest to the isoelectric point. Exactly, at the pH farther away from the isoelectric point. Wherever you can get that's farther away from the isoelectric point, that's where the protein is going to be most dissolvable. At what pH is the protein going to be least dissolvable? Not just closer, at the isoelectric point. Exactly. Very good, very good. Okay. Have a great day, you all.